protection. So we finished the overcurrent protection, and now we will take an overview about the distance protection, the operating principles, the backup methods, and how to implement the zone reach and time grading in our protection testing, and how also to configure the distance REO file, and we will take some examples. Okay, so firstly, we will talk about the operating principle about the distance protection. So the operating principle of the distance protection function is that the distance protection function uses a combination of a current and a voltage as a criteria to differentiate between normal operating states and fault states. So the distance protection relays are applied as a short circuit protection in almost all the systems. Okay, so whereas the overcurrent relays cannot be used for reasons of selectivity, or if there is a need for short tripping times, we shall use the distance protection. Okay, so the background knowledge here is the distance protection function works with the impedances. Okay, so it uses the impedance as a criteria to distinguish between the normal operating status and the fault status. So from the measured values of the current and the voltage, the relay can calculate the impedance according to the following formula, which is Z measured equal to voltage measured divided by I measured. So as you can see here, current and the voltage will be measured using the CT and the VT. Okay, and the relay will use this measured values of the current and the voltage to calculate the impedance. And if this impedance falls below a preset value, which can be identified in zone 1, zone 2, zone 3, will start the distance protection, and after the time elapse, it will issue a trip command for the circuit breaker if we have any fault condition like this. So during the normal operation, the voltage is about the nominal voltage, which is available in our power system, yes? And the current is will be in the range of the load current, which means from 0 to I rated, for example. So the impedance that measured in this case will be a very large value, which will be located in the loading area, okay, which means there is no fault and the relay works in the normal operating conditions. But in case if we have any short circuit on the line, the voltage of the faulty phases will drop drop off, will be a very small value, and the current in the fault phases increases, which means the measurement here, or the Z measure, will be low value, smaller value, and if it falls below the preset value of Z1 or Z2 or Z3, it will start to initiate a timer, and after this trip time elapses, it will issue a trip command. So for example, here we have a fault, and the Z measured here is the Z short circuit, okay, which is the V short circuit divided by I short circuit measured by the protection relay. So the relay will measure this impedance of the short circuit fault, and it will also calculate the fault location based on the line parameters as a percentage from the line or in kilometer. Yes. So the ZSC here is proportional to the distance of the fault. So the longer the distance, the impedance will be higher. Okay, because it depends on the parameter of the line. So the closing fault, the ZSC will be small, but for the far off faults, the short circuit impedance will be a very large value and can be located for Z2 or Z3, which means it will have like a trip time delay for 400 milliseconds or 800 milliseconds to allow the main protection to trip the fault current. Okay, so here is the selectivity will detected by the trip time, which is depending on the fault distance or the fault location. Okay, now we will talk about the short circuit current and short circuit voltage. As you can see here, is we have some parameter. If we can represent the short circuit impedance in a single line diagram, so we have the short circuit voltage, the short circuit current, and the Z short circuit, which is impedance. Short circuit impedance is a value of short circuit voltage divided by the value of short circuit current, and it can be classified into two parameters in the real and imaginary impedances. As you can see here is the resistance and the inductance. So the short circuit impedance in this case will calculate the short circuit angle, which is equal to the line impedance. Okay, so the Z line and the line angle phi line. In this way, by calculating the impedance, the distance relay can not only distinguish between the operating state and the fault state, but it's also able to locate the occurring fault, which means the relay is able to determine the fault location. As you can see here, how to represent the resistive part of the short circuit impedance and the reactive part of the short circuit impedance. So if we have a resistive load, purely resistive load, so the voltage and the current will be in phase, which means there is no voltage difference between, there is no phase angle difference between the voltage and the current. But if we have inductive reactance, as you can see here, so the current will lag the voltage by angle of 90. So the combination between resistive and reactive load, which is happening in the most commonly overhead lines and underground cables. So here is the relation between the short circuit current and the short circuit impedance. And here is the phi 1 is the phase shift between the voltage and current angles. Okay, so here is, if located here, it will be in the forward current direction, and here is the reverse current direction, and real and imaginary simulation. Now we will talk about the short circuit impedance itself. So we have impedance diagram and distance zones. So the impedance can be visualized in the complex plan, as you can see, with real and imaginary axis, or RX plan. And here is the short circuit current, the short circuit voltage, and the phase difference between both of them. So the impedance of the line is ohmic inductive, okay, which means the line characteristic is then located in the first quadrant for the complex impedance plan. But how to form this RX plan using the vector values? So depending on the operational line characteristic, which is R line and the X line. Okay, so the Z here, which is can be represented in a polar form with angle phi Z equal to amplitude of voltage with angle phi voltage divided by amplitude of current with angle phi current. So the resulting from this equation will be the amplitude of voltage divided by amplitude of current, and the angle will be the phase difference between phi V and phi I. Okay, so here is how to represent the short circuit impedance in the RX plan. So for example, if we have the phi voltage equal to 0, which is the reference value, and the phi Z in our case will be minus phi I. So the forward fault lines will be in the quadrant 1, and the reverse will be in the quadrant 3. And the fault impedance, for sure, is proportional to the fault distance, because it depends on the line length of the fault, or the short circuit impedance depends on the location of the fault. Okay, so here is the ZSC with phi Z, and here is the forward fault impedance in the first quadrant, and the reverse fault impedance will be located in the third quadrant. Okay, and here is the line characteristic, as you can see, and here is the 100% from the Z line. Here is represented the total line length. Okay, so here is the horizontal segment here represents the total line impedance, okay, without any fault, which is located for sure in the first quadrant. Okay, but if this fault distance is increased more than 100% from the line length, it will be located in Z2 or Z3 based on the relay parameter setting. Now we will talk about how to make time grading between zone reaches, and to provide the selectivity and of our protection system, and also to prevent the unselective tripping. So at our example here, we see the line with a 3 section. So with each section is protected by a distance protection relay. Okay, so we will focus now on the distance relay in the section A. As you can see here, we have the incoming feeder, we have bus A, bus B, bus C, and here we have circuit breaker A, circuit breaker B, circuit breaker C, and different relays also for each line segment. So the relay A should protect the section A as a main protection, and it will act as a backup protection for section B and section C. Okay, so for this reason, we have several zones are parameterized here. So zone 1 protects 85% from the line A, and if the line fault occurring in the area will be cleared with an instantaneous trip time delay, which is the trip time delay of zone 1 equal to 0 millisecond. And if we take into consideration the internal processing time of the protection relay will be around 30 milliseconds. But due to the measurement inaccuracies, and also to prevent the unselective tripping, zone 1 doesn't cover 100% from the line A. Okay, so zone 2 in our example also will reach until 120 from the line A, or it will reach like in the middle of line B. And the trip time delay here is set to 400 milliseconds, for example, just to give the time to relay B to relay A, which is the main protection for the section B or section A. Okay, so the main protection should trip firstly with instantaneous tripping, and zone 2, zone 3 will be delayed by 400 milliseconds and 800 milliseconds respectively. Okay, so here how to define the time grading between the Z1, Z2, and Z3. Okay, so the higher zones will have higher tripping times, just to allow the main protection to act as a main protection and to trip instantaneously. Otherwise, it will trip, but with a time delay equal to 400 or 800 milliseconds, and it will act as a backup protection in this case. Okay, so we have here the grading factor, which is 85% to avoid the unselective tripping and also to avoid the measurement inaccuracies in the terms of line impedance. Okay, and also it works in the we have some zones which operate or works only in the forward direction, like zone 1, zone 2, zone 3, which is the tripping zones. And also in some relays we have like non-directional pickup, which can be used for phase selection or power swing, for example, to detect the starting of power swing based on the impedance trajectory. Okay, so here is how to define the distance protection characteristics. So here is the zone, as you can see in our single line diagram, can be also visualized in the complex plane or RX plane. So here we have here is the line characteristic, and here is the line angle. This line angle is calculated and measured before we start the testing and commissioning in the design stage, and based on these parameters of the line, we can calculate the Z1 and Z2 and Z3. So generally the distance zone exists in different shapes. So it depends on the country or depends on the local practice. You can use different shapes of the distance zones. Okay, for example, we have the polygon characteristic is very common used and widely used in our area. Okay, and this polygonal characteristic is limited by the directional lines. As you can see here is the directional lines which to identify the forward fault and the reverse fault. Okay, so here is the directional lines also can be limited by the reach along the protected line. So here you should have Z1 protecting 85% from the line with a trip time instantaneously equal to 0 millisecond. Then we have Z2, which can cover 120, for example, from the line length with a time delay equal to 400 millisecond. And Z3 can cover 200% from the line length with a time delay equal to 800 millisecond. Okay. Also, we have another parameter here called the arc resistance. So if you have a single phase to ground fault, we will have another parameter called the arc resistance, which is resistance from the fault location out to the ground. Okay, so it can be represented in the horizontal line, as you can see here. And now you can define the zone by 4 lines: zone 1, zone 2, zone 3, as you can see. So here is the characteristic also can be drawn in a polygonal characteristic or a circular or moho shape or elliptic shape, which called tomato shape. So we have different shapes to represent the distance protection characteristic. Now we will talk about the distance system setting available in the protection setting and how to calculate of the Z line and the X line and the R line. And from the protection relay, for example, here we have the line length in ohm equal to Z line. We have the line angle equal to 64, which is measured in the design stage. And we have also the X line. But what if we have the X line as a parameter setting and we need to calculate the Z line? So simply we can use the formula X line equal to 0.218 ohm per kilometer multiplied by the line length, which is 32.5 kilometers. So we will have the X line total 7.085 ohm. Okay, so here is the total X line or the total inductive reactance of the overhead line. But now I need to calculate the Z line. So we can use the mathematical formula here, which is a sine of the line angle equal to X line divided by Z line. So we can calculate now the Z line equal to X line divided by sine of the angle. So it will equal to 7.883 ohm. Okay, so in some relays like Siemens relay, the line impedance is represented in X line in ohm per kilometer. So to calculate the total impedance of the line, you have to use this mathematical formulas to able to define and to calculate the total line impedance. Okay. We have also another parameter called the PT connection, and this PT connection, potential transformer, is the same as voltage transformer. So the PT connection can be connected on the line, as you can see here, and can be connected also at the bus bar. But what is the difference for the CMC in both cases? The main difference here is if the voltage connection is connected at the line, so if you have any post-fault stage, the CMC will not simulate any post-fault voltage because the circuit breaker is tripped and there is no meaning to inject any voltage in the post-fault stage. Okay, so it makes sense to interrupt the post-fault voltage by the CMC. But if the PT is connected at the bus bar, this means if we simulate a post-fault stage, so the CMC will continue to output the voltage at the rated voltage because the circuit breaker will be tripped, right? But the bus bar voltage is still healthy. So here is the main difference between the PT connection at the line at the bus bar. So you have to identify and configure this setting in the distance array file based on the connection schemes or the drawing inside your substation. Okay, we have also another parameter called the CT start point, which we explained in the instrument transformer slides, Okay, so we have a CT star point, okay, which is the grounding of the CT star point. Is it towards the object or towards the bus bar, which is a very integral part to define the forward and the reverse faults. We have also another factor here, which is called the grounding factor. So if you have a face-to-face voltage, so the distance between the relay and the fault can be calculated from the loop impedance, just using the line impedance, which is a short circuit impedance, okay? But if you have a face-to-ground fault, the ground impedance, ZE, must also be considered, okay? So here the Z short circuit in the loop will be the short circuit impedance plus the ground impedance. So to take the ground impedance into our consideration, the zero sequence compensation factor, which known as a grounding factor, is used, okay? Here is the definition of the factor depends on the vendors, okay? So different from vendor to another. For example, here, if in case of you have a face-to-face volt, only Z line is in the loop, so the correct impedance measurement doesn't affected by the grounding factor. But if you have a face-to-ground fault, you will have ZE, which is a ground impedance, is a part of the loop. So the Z here will be equal to short circuit impedance or Z line plus the ZE, okay, to complete the path of the fault current between the phase and the ground part. Okay, so to represent this effect in case of single phase to ground, we have one factor called the grounding factor. And this grounding factor can be simulated using different ways. As you can see here, can be in the polar form, which is magnitude and angle, can be RE over RL and XE over XL, which is a ground resistive reach over the line resistive reach, and the ground reactive reach over the line reactive reach, or also can be simulated in Z0 over Z1. Z0 is the zero sequence impedance, and Z1 is the positive sequence impedance. So it depends on the vendors. So for Siemens relay, for example, it's using the RE over RL and XE over XL. But for EBB, for example, using the zero sequence impedance divided by the positive sequence impedance. For some other relays like Alstom, Arriva, Socratic for Siemens, SEL, they're using also the polar form, which is magnitude and angle. So here is another sorry. Here is another factor just to take it into consideration. We have another pickup methods also for detecting the starter logic of the impedance protection. So how to detect the pickup or the start of fault detection? We have different kind of starter logic. So the purpose of the starter logic function is to distinguish between the normal operating state and the fault state. So the starter function must ensure a high sensitivity and also a phase selectivity. So as soon as the relay picks up, independent of the actual starter logic, it evaluates and calculates the impedance. And if this impedance in one or more trip zones, the timer of this respective zones will be initiated. Okay, and as soon as the timer has elapsed, the relay will issue a trip command to trip the circuit breaker according to the setting trip time delay. Okay, so we have three general types of starter logic for distance protection. The first type is the overcurrent, which is the I greater pickup. So the overcurrent pickup here uses the current as a criteria to distinguish between the normal operating state and the fault states. So the pickup logic here is only applicable if the current can be used as a single criteria, okay, to differentiate between both operating and fault states. We have also another starter logic which called the V over I. So the voltage controlled overcurrent pickup, V over I, can be uses the current as a function of the voltage. So it will use the current measurement and the voltage measurement as a criteria to differentiate between the normal operating state and the fault state. So the VI characteristic, as you can see from our screen, is defined by three parameters, which is I greater, I double greater, as you can see here, and V greater. Okay, so since the voltage is less than this value and the current is greater than this value, it will be located in the pickup area, which means the distance protection will be started, will be picked up, and if the time elapsed, it will be trip circuit breaker after the trip time setting. Okay, we have also another starter logic called the impedance pickup, and the impedance pickup is mainly depends on the Z or impedance value. Okay, so if the impedance pickup uses the impedance as a criteria to differentiate or distinguish between the normal operating state and fault state. Okay, so we have here the pickup zone, which is defined in the complex or RX plane, and the blue area here indicates the blender or the load blender. So if the impedance is located inside the pickup area, the timer will be initiated and the impedance will be triggered or will be picked up. Okay, so here is the different types of the pickup methods or the starter logic, which can be used in the distance protection functions. Okay, so the most commonly used is the overcurrent pickup to use the current as a single criteria. For example, Now we will talk about the different types of zones. So based on the distance array file available in the test universe, we have different types, or we have different types of zones are available. Okay, the first type is tripping zones. Tripping zones, which can be represented in Z1, Z2, Z3, which means if the impedance located in each one of these zones, the timer will be initiated and the trip time will be issued after a time delay in the parameter setting to trip the circuit breaker and to isolate the fault. So here is the first type, which is called tripping. Okay, we have the second type of zones, which is the starting zones or the impedance pickup zones. So this zone causes starting only, which means it will not cause a trip command for the circuit breaker. Okay, so it's only a starting zone. It's possible to define a range of the impedance plane in which the starting will be followed up by a triggering with a maximum operating time, such as the phase selection zones in the ABB relays, for example. Okay, the third type of zones here, which is the extended zone. This zone is a tripping zone, but it's only activated occasionally. Occasionally means by means of some events, such as the manual close command detection. So it will, as you can see here is the dotted line, it will activate this extended zone to simulate and to protect the line by using the switch on to fault function. Okay, so the switch on to fault function or the extended function is a tripping zone, but it's only activated by a particular event. Okay, we have also another zones called the non-tripping zones, which is the load blender. So this load blender can be a non-tripping zone, but even if it's overlapped with a tripping zone, this zone is used to model the load blender or the load blending. Okay, so it's a non-tripping zone. As you can see, if it's intersected with the starting zone or the protected zone, it will be limited, the protected zone Z1, Z2, Z3, by the load encroachment or by the load blender. Okay, now we will take an example in numbers just to be clear for everyone. So we have 3 zones. Here is the directional lines to identify represented in R and X plane. So for example, Z1, the R value is 2.9 ohm and the X is 6 ohm, and the trip time is 0 millisecond, but you will not have 0 millisecond exactly because you have to take into consideration the internal processing time of the protection relay, which can be 30 milliseconds, around 30 milliseconds. We have also the other zone, which is Z2. For sure, the R and the X reach will be higher than the Z1 R and the X reach because it's covered 120% from the line. For sure, the R value and X value will be higher than the Z1, and the trip time 400 milliseconds. Z3 also 5.4 ohm resistive reach and 11.2 ohm reactive reach with a time delay 800 milliseconds. And if you have extended zone, which can be Z1B in dotted lines, so it will be equal to 4.1 ohm, 8.5 ohm, and 0 millisecond, but it will be activated occasionally based on the manual close command of the switch on to fault. Also, we can have a forward zone and non-directional zone with a different trip times. So as you can see here, it's Z line, here is the R reach of Z1, here is the X reach of Z1, the same also for Z2 and for Z3. Okay, then you have a Z1B, which is the extended zone, which can be simulated for switch on to fault, for example, as can be occasionally triggered or initiated using the manual close command of the circuit breaker. And also here is the line angle, which can be 64 degrees based on the calculation and based on the line measurement parameters. Okay, so the zone geometric depends on the manufacturers. So for example, for the Siemens relay, the directional lines can be represented in these 2 lines. This line, which is located in the 4th quadrant, have angle -22, which means 338 degrees. And the other line here in the 2nd quadrant, as you can see here, is 30 degrees plus 90, so it will be 120 degrees. Here is the Siemens relay. And as you can see, here is the X reach, here is the R reach. And if you extend this line, it will intersect with the -R axis in -R value. Okay. On the other hand, for the Arriva and Schneider and GE relays, this angle can be, it will be 45 degrees. So it's based on the relay vendor and based on the relay manufacturer, you can define the directional lines to identify the zone forward and reverse directions. For EBB also, it will be like Siemens relay, but it's with a different shape, as you can see. So also the forward directional angles here, -22 and 120. Okay, now we will see how to do the wiring scheme, the wiring check, or the wiring scheme using the CMC for the distance protection. For example, we have here line A and B. We have two relays here, two CT and two VT. Here is the protection relay is connected to the CT and the VT from the primary side. Okay, so we can inject voltage through and current through the analog input of the protection relay to simulate the primary and primary current and voltage in the overhead lines. And then we will wire the binary output of the protection relay to the CMC binary input to detect the backup signal or the trip signal, which is the response of the protection relay. Okay. Also, it's optional to wire the binary wiring between your CMC and between the protection relay for distance protection. Okay, so here's another example here. So we will wire the 3 voltage channel to the analog input voltage of the protection relay and the 3 current channel to the analog input current channel of the protection relay, and we will use the CMC binary input to be connected to the relay binary output to check the backup signal and the trip signal. Okay, so here is the different modules which can be used in a standalone module and also can be combined in the same OCC file to have automatic testing plans or a pre-configured testing plans. Okay, so we can use a ramping for pickup and drop off. For the starter logic, we can use a VI starting if you have distance starter function V over I. We have also the advanced distance protection, which can be used for detecting the impedance, trip time, and zone reach. Also, we have the auto closure. If you have 79 protection relay, you can simulate the auto closure sequences, successful and unsuccessful auto closures. We have this sequencer and quick CMC, which can be used in general mode to simulate any kind of event such as trip times of distance protection or switch on to fault or synchro check and so on. Synchro check also we have a dedicated testing module called the synchronizer, which can be used also by the sequencer or the quick CMC. So the advanced distance module here, which is our dedicated testing module, offers a several option to test the distance protection parameters. So we will see now how to check or how to use the advanced distance module to check the short test for testing trip times and the check test mode, which can be used for check the zone reaches, and the other option for zone reaches called the search test. Okay, so we will simulate different fault types, different fault loops to allow you and to show you how to test the distance protection using the advanced distance module. Okay, so here is the required and relay required docs. If you are starting from scratch, you can find out the general shape of the impedance using the relay manual, and also you can check the relay parameter setting available inside the protection relay. You can export it using the the relay software. Then you can import it inside the OCC file to make a predefined and customized test plan. So now we will, it's the end of our presentation.